In this video, you will learn the properties of matter. If you are new to this channel, please do not forget to subscribe, hit the bell, and do some comments. I post educational videos twice a week, every Tuesday and Thursday. So, let's get started. Our lesson for today is lesson 6.1, Properties of Matter, with the following goals: to define matter and identify the states of matter. Goal number 2, to describe the properties of solids and to solve problems involving Hooke's law and density of solids. What is matter? Matter is anything that occupies space and has mass. Mass is a measure of the amount of material the object contains, and volume is a measure of the space occupied by the object. Everything is made of matter. What are the three states of matter? We have solid, liquid, and gas. Solids have the following characteristics. They have definite shape, definite volume. The particles in solids are close together, they are fixed, and the particles move very slowly. Liquids have indefinite shape but definite volume. They take the shape of the container. The particles of liquids are close together but mobile, and the particles move slowly. Gases have indefinite shape, indefinite volume. They take the shape and volume of the container. The particles are far apart, and the particles move fast. Depending on the pressure and temperature, a solid can become a liquid by melting. The liquid can become a gas by evaporation. The gas can be turned back into liquid by condensation, and the liquid can be brought back into a solid by freezing. Properties of solids. Properties are words that describe matter. The following properties are common to solids. 1. Strength describes the ability of a solid object to maintain its shape even when force is applied. In figure 1, when a force is applied at the end of the bar, we can ask how much does the object bend or deform under an applied force. Also, given the force applied, we can also ask how much force can the object withstand before it breaks. Second property of solids, tensile strength. The tensile strength of a solid is a measure of its resistance to being pulled apart. Next property is hardness. The hardness of a solid is a measure of the internal resistance to scratching. Fourth property is brittleness. It is defined as the tendency of a solid to crack or break before stretching very much. Next property is ductility. A ductile material can be bent a relatively large amount without breaking. The ductility of many metals like copper allow them to be drawn into wire. Next property is malleability. Malleability measures a solid's ability to be pounded into thin sheets. Aluminum is a highly malleable metal. Next property is elasticity. This describes a solid's ability to be stretched and then return to its original size. Now we will study Hooke's law. One of the most basic principles related to the elasticity of solids is Hooke's law, named after Robert Hooke. According to him, the force required to stretch or compress a spring is proportional to the distance the spring is deformed, as long as the elastic limit has not been exceeded. In equation form, this law can be written as F is equal to K times delta X, where F is the applied force in newtons, delta X is the change in length in meters, and K is the elastic constant or the spring constant in newtons per meter. Here is a graph of Hooke's law showing the behavior within and beyond the elastic limit. The vertical axis is the applied force, horizontal axis is the change in length. This graph has two regions, the elastic region and the plastic region. The Hooke's law is applicable in the elastic region. The graph is a straight line going upward. When the elastic limit has been exceeded, the material becomes plastic. So that's why it's a plastic region. If we continue to apply a force after the plastic region, the breaking of the material will usually occur. Elastic limit is defined as the maximum stress that a material can withstand before the permanent deformation. It is the highest limit of the material before the plastic deformation of the material can occur. Once the stress or force is removed from the material comes back to its original shape. Hooke's law can also be applied to determine the restoring force required to compress or stretch a spring. In this case, the formula form of Hooke's law is F is equal to minus K times delta X, where F is the restoring force of the spring in newtons, K is the elastic constant in newtons per meter, and delta X is the change in length in meters. The minus sign is there to show that the restoring force is opposite of the deforming force. The spring tries to restore itself to its undeformed state. When a spring is pulled apart, the spring pulls back against the force of the pull, as can be seen in the figure below. When a spring is compressed, the spring pushes back against the compression. Let us do some examples now. Example number 1. How much force is needed to pull a spring with a spring constant of 20 newtons per meter, a distance of 25 centimeters? Solution. Here, spring constant K is 20 newtons per meter and the delta X is 25 centimeters or 0.25 meter. Since we are looking for the force required to pull the spring apart, we use the formula F is equal to K times delta X, substituting values and simplifying. F equals 20 times 0.25 equals 5 newtons. So, a force of 5 newtons is needed to pull this spring a distance of 25. Example number 2. A spring is pulled to 10 centimeters and held in place with a force of 500 newtons. What is the spring constant of the spring? Solution. Here, delta X equals 10 centimeters or 0.10 meter. The force is 500 newtons and we are required to find the spring constant K. From the formula F equals K times delta X and solving for K, we get K equals F over delta X. Substituting the values and simplifying, we have K equals 5,000 newtons per meter. Example number 3. What is the spring constant of a spring that needs a force of 3 newtons to be compressed from 40 centimeters to 35 centimeters? Solution. Here, delta x is 35 centimeters minus 40 centimeters. That is, final length minus the initial length is equal to negative 5 centimeters or negative 0.05 meter. The force here is negative 3 newtons because it is a compressive force, and we are required to find the spring constant K. So, from the formula F equals K times delta X, and solving for K, we get K equals F over delta X. Substituting values and simplifying, we have K equals 60 newtons per meter. Springs in parallel. Two or more springs are said to be in parallel when used as in the figure below. For springs which are used in parallel, the equivalent spring constant K sub AQ equals K1 plus K2 plus K3 plus and so on plus K sub n. The Hooke's law formula becomes F equals K equivalent times delta X, or F equals negative K equivalent times delta X when it is a restoring force. Example number 4. What is the magnitude of the force required to stretch two springs of constants K1 equals 100 newtons per meter and K2 is 200 newtons per meter by 6 centimeters if they are in parallel? Solution. Here, delta X is 6 centimeters or 0.06 meter. Equivalent equals K1 plus K2 equals 100 plus 200 or 300 newtons per meter, and we are required to find the force F. So, from the formula F equals K equivalent times delta X, we have F equals 300 times 0.06 is equal to 18 newtons. Springs in series. Two springs are said to be in series when used as in the figure below. For springs which are used in series connection, the equivalent spring constant KEQ is found by solving 1 over KE equivalent equals 1 over K1 plus 1 over K2 and so on plus 1 over K sub n. The Hooke's law formula becomes F equals KEQ times delta X, or F equals negative KEQ times delta X. Example number 5. What is the magnitude of the force required to stretch two springs of constant K1 equals 100 Newton per meter and K2 equals 200 Newtons per meter by 6 centimeters if they are in series? Here, delta X is 6 centimeters or 0.06 meter. Solving for the equivalent spring constant K sub AQ, we have 1 over K sub AQ equals 1 over K1 plus 1 over K2. Substituting values and simplifying, 1 over K EQ equals 0.015. Finding the reciprocal, KEQ equals 66.67 newtons per meter. So, from the formula F equals KEQ times delta X, we have F equals 66.67 times 0.06 equals 4 newtons. Now, let's consider potential energy of a spring. To stretch or compress a spring by a length delta X, energy is needed. Once stretched or compressed, the energy is stored in the spring as potential energy PE and is given by P sub E equals 1 half K times delta X squared in joules. Example number 6. How much energy is needed to compress a spring from 15 centimeters to 10 centimeters if the constant of the spring is 150 newtons per meter? Solution. Here, delta X is 10 centimeters minus 15 centimeters, which is final length minus initial length, which is equal to minus 5 centimeters or negative 0.05 meter. The energy W to compress the spring will all be stored as potential energy PE in the spring. Hence, W equals P sub E equals 1 half K times delta X squared equals 1 half times 150 times negative 0.05 squared, and this gives us 0.1875 joule. Now, let's consider mass density of solids. What is mass density? Different substances may have the same mass, but they don't necessarily fill the same volume. Density is the measurement of how much mass is contained in a given volume. It is the measure of the compactness of the material. To calculate the mass density of an object, we use the formula D equals m over V, where D is density in grams per centimeter cube or kilograms per meter cube. M is the mass in grams or kilograms. V is the volume in centimeter cube or meter cube. In some instances, we are also required to find the weight density of solids. It is the measurement of how much weight is contained in a given volume. To calculate the weight density of an object, we use the formula D equals W over V, where D is density in dyne per centimeter cube or newtons per meter cube. W is the weight in dyne or newtons, and V is the volume in centimeter cube or meter cube. Example number 7. A small block of wood has a volume of 25 cubic centimeters and a mass of 20 grams. What is the density of the wood? Since the mass is given, then we are required to find the mass density. Using the formula D equals m over V and substituting, the final answer is 0.8 gram per cubic centimeter. Example number 8. Frank has a paper clip. It has a mass of 9 grams and a density of 3 grams per cubic centimeters. What is its volume? From the formula D equals m over V and solving for the volume, V equals m over D. Substituting the given values, we have V equals 9 over 3 is 3 cubic centimeters. Example number 9, Jack has a rock. The rock has a volume of 5 cubic centimeters. Its density is 2 grams per centimeter cube. What is the mass of the rock? From the formula D equals m over V and solving for the mass, mass equals the density times volume, and substituting the values, we get the mass is 10 grams. Thanks for watching. Please do not forget to subscribe.